So before we tackle this question, we're going to take a read through the whole thing, try and understand the language, figure out what topic it is, and what math knowledge we need to bring in to be able to solve it. So let's have a look. We've got a company is designing a logo. Great. The logo is a circle of radius 4 inches with an inscribed rectangle. Okay, so inscribed means that all 4 vertices of that rectangle must lie on the circle. The rectangle must be as large as possible. Large is a bit vague. We don't know if that means extra wide or perimeter or area, or who knows. We'll wait and see. The company models the logo on an XY plane as shown in the diagram. So they've put some axes on this. So I guess if it's a 4-inch circle, we could label an X value of +4 on that edge of the circle, a Y value of +4, -4, -4. So we've got a scale on what we're looking at here. And they've drawn an example rectangle inscribed in that circle. Okay, let's read on. Use calculus to find the maximum area of the rectangle. So calculus can refer to differentiation or integration. Now we're told to use calculus to find the maximum area. So first of all, that defines large in a more precise way. We're looking for the maximum area. And to find a maximum of a function, we know that we use differentiation. We get an expression for area, which we might call A. We then want to differentiate that expression. And for a maximum or a minimum, we want differentiation dA dx to equal 0. So this is not going to be an integration problem. When it says use calculus, here it means to use differentiation. Lastly, it finishes by saying fully justify your answer. So I think that's getting at the difference between a maximum and a minimum, proving that we've actually found a maximum using the second derivative. In terms of the textbook, these kind of questions come up in Blue Book 1, Chapter 12. At the end of Chapter 12, there's a section called Modelling with Differentiation, and exercise 12K, I think it is, has a couple more questions using calculus to find the maximum or minimum of some function. So let's make a quick plan, a strategy, and then we'll be able to do the algebra that we have to do to solve this. So we've got a 3-step strategy here. First of all, we're going to have to find an expression for the area of the rectangle in terms of x. That's probably the trickiest part. Then we'll differentiate that and solve it equal to 0 to try and find the maximum. And as we said, to justify this, we should use the second derivative to prove that we really have found a maximum. So let's start with step 1, finding an expression for the area in terms of x. Now we're going to need to know the equation of this circle. So it's a circle centered at the origin on radius 4. So its equation will be x squared plus y squared equals 4 squared. So x squared plus y squared equals 4 squared is 16. And we're going to rearrange that to y equals the square root of 16 minus x squared. Now, why is that so important? Well, we need to bring some variables into our diagram. So we're going to call the point where that rectangle reaches on the x-axis, I'm going to call that value x. And then the height, so to find the y-coordinate at that point up there, that will be the square root of 16 minus x squared. So its x-coordinate is just x, and its y-coordinate is the square root of 16 minus x squared. So when we think about area now, I've got a small rectangle. I'm just going to look at this small quarter of the whole rectangle, where its width is x, and its height is the square root of 16 minus x squared. And 4 of those altogether make the area of the whole rectangle. So I can write an expression for the area A of the whole rectangle is 4 of these small rectangles, and they have a width which is x, and they have a height which is square root of 16 minus x squared. So that there is a formula for, or an expression for, the area of the whole rectangle in terms of x, and that's the first step in our strategy completed. So let's make a bit more space now. We could move on to solve part 2 of our strategy, which is to now differentiate this function, solve that equal to 0 to try and find the maximum. Now again, let's plan ahead for this differentiation. If we look at this expression, or this function a, it's a product of two parts. We've got a 4x part, and we've got a square root of 16 minus x squared part there. So we need to use the product rule for differentiation, which is u dash v plus uv dash, where u is the first part and v is the second part. So let's have a go at that. dA dx equals, okay, u dash v. U dash is just 4, and v is not affected, so square root 16 minus x squared still. Plus uv dash, u doesn't change now, that's 4x. V dash, square root differentiates to 1 over 2 times the square root, 16 minus x squared. But now we've also got the chain rule. We have to multiply by box dash. The box is 16 minus x squared, and that differentiates to minus 2x. So I've used the chain rule there to differentiate the square root of a box. Square root of a box differentiates to 1 over 2 root box multiplied by box dash. So now we probably want to simplify this slightly, but also remember we're going to solve dA dx equals 0 in a minute. So I'm not going to do too much to tidy this up. We'll keep the first term as 4 square root 16 minus x squared. And let's just simplify this slightly. We've got a negative term now. The 2's cancel. We've got 4x squared over the square root of 16 minus x squared again. And now we want to make this expression dA dx equal to 0. And for our communication, we want to say, so for a maximum, dA dx must equal 0. Remember, you have to explain your strategy as well as just doing the maths along the way. Okay, let's make a bit more space and then we can solve that equation. So dA dx equals 0. So we go back to, we've got 4 square root 16 minus x squared minus 4x squared over the square root of 16 minus x squared equals 0. I think I'm going to multiply through by the square root of x 16 minus x squared. So we're going to have 4. Now when I multiply the square root by the square root again, we'll get 16 minus x squared. The next term, we're multiplying by square root of 16 minus x squared to clear its denominator. So it will just be minus 4x squared. And that equals 0, because even when 0 is multiplied by the square root of 16 minus x squared, it's still 0. Okay, we need a bit more space again. And we are just going to simplify that now. We've got 64 minus 4x squared minus another 4x squared, so minus 8x squared equals 0. 8x squared equals 64. So x squared equals 8. So x equals plus or minus the square root of 8. Now if we interpret that back to the original problem, we want x to be positive, and x is measured in inches. So I would say, therefore, x equals square root of 8 inches. Now let's have a quick look back to our goal. We've completed stage 2 in our strategy, so we can give that a tick on the list. Let's reread the question. Find the maximum area of the rectangle. Now I've only got an x value so far, so I need to substitute that x back into the area function to see what area that corresponds to. Let's zoom out slightly. We've got an x value of root 8 to substitute into the area. So let's do that on the side here. When x equals the square root of 8, the area equals 4 square root 8 times the square root of 16 minus x squared, and that's root 8 squared, which is 8. So I've got 4 times root 8 times root 8, which is 4 times 8, which is 32. You can put that in your calculator if you prefer. Let's give that some units as well. That will now be in square inches. Okay, so now we're completely done, but we mustn't forget we had a third step in our strategy, which was to justify that this is a maximum, and we're going to need the second derivative to prove that. Okay, let's go for it. We've got minus 4 root 8. And this bottom, we've got x squared is 8. 16 minus 8 is still 8. Square root 8 on the bottom. Minus, now we're going to have 8 root 8. And the square root of 16 minus x squared is another root 8. The bottom is 16 minus x squared. That's 8. There's 8s everywhere. Plus, and we've got a fraction in here. The bottom is root 8. And the top is 4x cubed. So that's 4 root 8, root 8, root 8. Now, why am I writing it like that? Well, it's because some of them will cancel. That will go. So the fraction's gone. And we can pretty much simplify this, or you might want to type it in your calculator. These root 8s cancel in the first term. In the second term, I'll just change colour so you can see what I'm doing. I can cancel the 8 on the bottom with root 8 in that term. They're gone. And root 8 in that term. They're gone. So the fraction is just 12. We've got minus 4 from the first term, minus 12 from the next term. We've got negative 16. And what's important right now is that that is less than 0. So therefore, we have found a maximum. We're done. We made it.